This is circuits number 2 video, and in this video we will look at RC circuits. So you will have capacitors and resistors in your circuit. So at first we're going to start with the capacitors. So the same as resistors, capacitors can be connected in parallel or in series. So in series connection, you have capacitor after the capacitor. So you have them all sitting on the same line. So you have one capacitor, next capacitor, next capacitor. It's the same as line as cars standing in a line. And in parallel connection, you have many lines and the cars are parked parallel to each other. So in this case, you have capacitors in parallel. So when the capacitors are connected in parallel, the same as with the resistors, they share the same potential difference. Because this point, if this point is A, so is this point, because there is nothing connected between these 2 points. And if this point is B, then so is this point is also B. So they share the same potential difference. So the same would be here, this is B, and the same would be here, this is A. So they all have the same potential difference, and their charge, the one that comes from the battery, is going to be distributed among all the capacitors. So the total charge on all the capacitors is the sum of all the charges on every single capacitor. So eventually you will have the same charge when the capacitors charged fully, the current is going to stop flowing. So you're going to have current floating from positive to negative for as long as the capacitor is being charged. When the capacitors are fully charged, then the current is going to stop floating. So the charge on all of these capacitors, the sum of all the charges, is going to be the total charge that was on the battery. And the same for the negative side is going to be the sum of all the charges that was on the negative side of the battery. And the same for the capacitance. When you had resistors connected in parallel, you wouldn't add them as resistor 1 plus resistor 2 plus the resistor 3. There would be a different rule. It would be 1 over, 1 over, 1 over, the result flip over, if you remember our lesson on the resistors in parallel. But capacitors are opposite. So for the capacitors, if they're connected in parallel, all you do, you add them. The same as if the resistors were connected in series, you just add the resistances. And when you have capacitors connected in parallel, you again add them. For series connection, so for series connection, I have all the voltages. So the voltage dropped on this capacitor, the voltage dropped on this capacitor, the voltage dropped on this capacitor. I'm going to call it V1, V2, and V3. So the total voltage, so this would be the total voltage, is the sum of all the voltages dropped on every single capacitor, the same as it would be in series connection for the resistors. The charge is going to be the same. So when the capacitors are fully charged again, the current is going to stop floating. So the charge on this plate is going to be the same as the charge on this plate, and it's going to be the same as the charge on this plate. And the same is going to happen for the positive charge, because it's connected to the positive plate of the battery. And the same is going to be the negative charge here is the same as negative charge here, and the same as the negative charge over here. And so the formula says the charges on every capacitor is going to be the same for the current to stop floating. If the charges are not the same, the current is going to still float. And for the capacitance, now in parallel connection of the resistors, we had 1 over, the result flip over. Now for series connection of the capacitors, we have 1 over, the result flip over. So the only thing that is actually different, big difference, is how you calculate the total capacitance of the circuit with many capacitors. In resistors, you would add them in series connection, and here you add them in parallel connection. And what you would have 1 over when you had resistors when they're connected in parallel, and here you have 1 over when you have capacitors connected in series. So let's look at some of the questions and see how we can solve them. So here's the first question we're going to look at, and in this case we have 5 microfarad connected parallel to 6 microfarad connected parallel to 12 microfarad and 24 microfarad capacitors. And we need to determine the total capacitance, or the equivalent capacitance of all the capacitors. And then we want to find the charge on the 12 microfarad capacitor and find the charge on the 24 microfarad capacitor. So at first I'm going to do the total capacitance. Because they're all connected in parallel, it's the sum of all the capacitors. So the total capacitance, or the sum of all the capacitors, or equivalent capacitance, is equal to 3 plus 6 plus 12 plus 24, which is 45 microfarad. So this is 45 micro 10 to the negative 6 farads. And then find the charge on the 12 microfarad capacitor. At first I need to find the total charge. So if I find the total charge, that is the voltage times the total capacitance, and the voltage is 18 volt, and the total capacitance is 45 microfarads. So the total charge is equal to 810 microcoulombs. The charge on the 12 microfarad capacitor is the voltage, which is the same, times the capacitance of the 12 microfarad capacitor. Because they're all connected in parallel, I still have 18 volt for every single capacitor, and then I times it by 12 microfarad, which is 10 negative 6, I will get 216 microcoulombs. And if I calculate the charge on the 24 microfarad capacitor, I have again the voltage, potential difference, times the capacitance of the 24 microfarad capacitor. That gives me 18 times 24, 10 to the negative 6 for micro, and I get 432 microcoulombs. I can do the same for 6 and 3. So if I calculated the charge on the 6, they don't ask me, I just want to show you. So that is again the voltage times 6 microfarad. So that will give me 108 microcoulombs. And if I calculated the charge on 3, that would be 18 times 3 microfarad. And this will give me 54 microcoulombs. Now, from the rule that I just described earlier, the sum of all the charges on every capacitor should give you the same as the total charge on all the capacitors. So if I add every single charge on every capacitor, I should get 810 microcoulombs for all capacitors together. Here we have capacitors connected in series, so I have to calculate the equivalent capacitance of all the capacitors. So here I have to do 1 over of the equivalent capacitor, so I can use E for equivalent, or the sum sign is equal to 1 over, so I have to have 3 micro 10 to the negative 6 plus 1 over 6 micro plus 1 over 12 micro and plus 1 over 24 micro. So that gives me equivalent capacitance is equal to 1.6 microfarad. If I was looking for the total charge, equivalent charge for all the capacitors together, and they have the same charge, so I will have the voltage times the equivalent capacitance, and again I have 18 times 1.6 micro, and that will give me 28.8 microcoulombs. So they all have the same 28.8 microcoulombs on every single capacitor. because they share the same charge. So I can say that the charge on the 12 microfarad capacitor is 28.8 microcoulombs, and it's the same as the charge on the 6, it's the same as the charge on the 3, it's the same as the charge on 24, so they're all the same. And then they ask you find the voltage. So the capacitance is equal to how much charge per potential difference. So if I want to find the voltage dropped on the 12 microfarad capacitor, so that will give me the charge on the 12 microfarad capacitor divided by the capacitance of the 12 microfarad capacitor. So I have the charge is 28.8 microcoulombs divided by the capacitance, which is 12 microfarad. Micro and micro will cancel, and I have 2.4 volt is dropped on 12 microfarad capacitor. So if you measure the voltage between those 2 points, you have 2.4 volt right here. And then you can calculate the same. So if I wanted to calculate the voltage on, let's say, 6 microfarad capacitor, it's going to be the same charge for all of them. So that's 28.8 microcoulombs divided by the charge, by the capacitance of the 6 microfarad capacitor, which is 6 micro. So that will give me the voltage on the 6 microfarad capacitor, the drop. So if I measured the voltage on this capacitor, that would give me 4.8 volt. And again, if I do the same for every single capacitor, when I add all those voltages, it should give me 18 volt, the total voltage of all the capacitors or the battery. You will never have anything this complicated on your exam, but I just want you to see how to recognize the patterns and how to solve for equivalent capacitance. So here on, I'm going to do them in different colors. So on the red line, I have 2 capacitors connected in series. And if I do the series connection, I do 1 over, the result flip over, and each one of them is 1 micro. So my equivalent capacitance for the red one is going to be 1 over, so it's 1 over 1 micro, plus 1 over another micro. So the total capacitance for the red ones is going to be 0.5 microfarad. And because the next one also has 2 in parallel, so for these ones I have another, so this was the top ones, and here I have the node for connection. And for this one I also have 0.5 microfarads. Then I see another one that has all in series, 2 in series, so these 2 I also can rewrite as 0.5 microfarads. So I'm going to redraw my circuit now, and I'm going to write, so here is A and here is B. So I have point A, point B, and here I have the capacitor of 0.5 microfarads. Then I have another one of 0.5 microfarads, and then I have the third one of my 0.5 microfarads, and in between these I still have one. I'm gonna make this one in blue. I still have one that is 1 microfarad, so this is 1 microfarad. Now all these guys are connected in parallel, and actually point 1 and point A and B is the same point. I don't even have to write it here. So all of them are connected in parallel, so now I can just have to add them. I don't have to do 1 over. So I have 0.5 plus 0.5 gives me 1 microfarad, add another 1 microfarad gives me 2 microfarad, and add another one gives me 2.5 microfarad as the total capacitance of all the capacitors connected in this circuit. So here's one more question that we can look at with a combination of series and parallel connection of the capacitors. So first we need to find the equivalent capacitance between the point A and B. And for that, at first we're going to get rid of the parallel connection. So here I have parallel connection. For parallel connection, I just add them. So I'm going to redraw my circuit as, so the first one has 4 microfarad. So here I have 4 microfarad. Then the next one, I just have to add them. So this one is also going to be 4 microfarad. And then 6 and 2, they are again in parallel. So I only add them when they are parallel. So that gives me 8 microfarad capacitance. And then I have another 8 microfarad capacitance. And here is your point A and point B. So because these guys are connected in series now, I have to do 1 over 1 over, the result flip over. So if I do 1 over, I have 1 over 4 micro plus 1 over 4 micro, which is the same as 4 10 to the negative 6 plus 1 over 4 10 to the negative 6. So this will give me, I'm going to redraw the circuit. On the top, it will give me 2 microfarad on the top. So 2 microfarad on the top. And the same I will do for the bottom one. So it's 1 over, now I'm going to have 1 over 8 microfarad, 1 over 8 microfarad, 1 over 8 10 to negative 6, 1 over 8 10 to negative 6. So I'm going to get 4 microfarad right here when I calculate the total capacitance. So here is point A and here is point B. And that is 1 over the total capacitance. So that I have to flip it over at the end. So it's 1 over the result, flip over. So now they are in parallel. And because they're in parallel, all I have to do is just add them. So if this is point A and this is point B, if I just add them, then I will have the total capacitance is 6 microfarad. So this would be my final result. For A, calculate the equivalent capacitance between point A and B, so that is 6 microfarad. Now they're saying, what if we connect the battery to point A and B? So I have the battery positive, negative, and connected here, and the battery is 12 volt. They want you to calculate the charge across the 4 microfarad capacitor. So if the battery is connected right here, and it is 12 volt, I want to calculate the charge on 4 microfarad capacitor, the first one. So because between point A and B I have 12 volt, and the total capacitance is 12 micro, 2 micro. So the total capacitance of these two guys right here on the top, 2 micro. Then I can find the charge on both of them. So the charge on the top line, I mean this line, the top one, I'm looking at this line, and the charge on both of them together. So that is equal to the total capacitance, which is 12 micro, times the voltage. And the voltage is the same because this branch is like this branch and this branch, they connected to 12 volt battery. So those 2 points. So between these 2 points, you have 12 volt. So that is 12. So that gives me 24 microcoulombs of charge. And because they are in series, they all share the same charge. So that means the 4 microfarad capacitor has the same 24 microcoulombs of charge, and the voltage on it is equal to the charge, which is 24 microcoulombs, divided by the capacitance, which is 4 microfarad, and gives me 6 volt. So the voltage drop on the top capacitor right here is going to be 6 volt. So it takes time for a capacitor to fully charge. So the following graph, where you have the charge over time, represents the graph of the charge of the capacitor while it is attached to a voltage source. The dotted asymptote represents the capacitor's final or maximum allowed charge, and the Q final is the maximum charge that it can have. And then the capacitor is placed in a circuit with the, if the capacitor is placed in a circuit with a resistor, then you have RC circuit. Then you can calculate the time it takes for the capacitor to charge by using this formula where tau, this letter tau, looks like this. It's in seconds. You can calculate by R times the capacitance C. So in RC charging circuit, the time constant tau value needs only 63% of the total maximum capacitance to be considered charged. So when the capacitor reaches its 63% of the maximum charge, it's considered to be fully charged, or the current through the capacitor almost drops to zero before it disappears completely. So here I've made an example for you of the circuit, and I want to, so there's a switch and 12 ohm resistor and 6 microfarad capacitor and 9 volt battery. And I want to know, right after the switch is closed, right after, I want to know the charge on the capacitor. So I will be calculating the charge on the capacitor. So that's the one that I'm looking for. And I want to know the potential difference on the capacitor, so the voltage dropped on the capacitor. So I'm looking for that part. And I am also looking for the current through the circuit. So I'm going to be looking for the current through the circuit and the potential difference across the resistor. So the potential difference across the resistor. So these are the things that I want to calculate in my problem. And the current is going to be flowing from positive to negative. So your longer line on the battery is the positively charged plate, and then, or charge side, and then the shorter one is the negative charge side. So at first, as soon as the switch is closed, the circuit is going to have some current, and the current is going to flow until the capacitor is fully charged. As soon as the capacitor is fully charged, the circuit is going to not have current anymore, because the positive plate or positive side of the battery is going to reach the same charge as the plate of the capacitor that's connected to the positive side, and the negative side of the battery is going to be reaching the same charge as the negative side of the battery charge. So as soon as the switch closes, then you have the maximum current flowing through the resistor, but there's going to be no charge yet on the capacitor. So to calculate the maximum voltage, I look at the capacitor, and if it was just the wire, like if there was no capacitor, then I will have Ohm's law from AP Physics 1, voltage divided by the resistance. So I have 9 divided by 12, or 3/4, which is 0.75 amps. So that's going to be the maximum current in this circuit at the moment when I just closed the switch. And the voltage dropped on the resistor at this moment right after the switch was closed, and is equal to 9 volt, because that's the voltage you have in the circuit. So all that voltage is going to be dropped on the 12 ohm resistor. So that is what's happening right after the switch is closed. Now, so I'm going to call this time equals to 0 seconds when the switch just got closed. Now, when the time is equal to infinity, that's long time after the capacitor has been fully charged, then the current at that point is going to be equal to 0 amps, because the capacitor is going to be fully charged by that time, and because there is no potential difference between the battery and the capacitor, so there's going to be no current flowing at that moment. And because there's no current flowing through the circuit, then the voltage on the resistor is also equal to 0. If the voltage on the resistor is equal to 0, then the voltage on the capacitor matches the EMF or the battery and equals to 9 volts. So from here I know that the capacitance is equal to charge per voltage, and I can figure out the charge on the capacitor as the capacitance times the voltage. The capacitance is 6 micro and the voltage is 9. So the charge on the capacitor long time after the switch has been closed and the capacitor is fully charged is 54 microcoulombs. If I want to calculate the time it takes for the capacitor to fully charge, tau, it's R times C. So R times C. R is 12 and the capacitance is 6 micro. So tau, the time to fully charge the capacitor, is 72 microseconds. So I would use these calculations right after the switch is closed, when I have the current, so I have the maximum current through the circuit and the voltage on the capacitor is still 0. And I would use, so this is for the time before 72 microseconds. And I will do these calculations for the time past 72 microseconds. On AP exam, on this type of questions, they will say, what happens right after the switch switches? So when they say what happens right after the switch switches, then you have to do these calculations. If they say what happens in the circuit long time after the switch was switched, so you do these calculations because the capacitor is fully charged. So there's like 2 questions to every single question where you have the resistor and the capacitor. It's before the capacitor is charged, which is determined by this formula, the time, so by this formula, and after the capacitor has been fully charged. So the top calculations before the capacitor was charged and the switch just got closed, and the bottom calculations after the capacitor has been fully charged and there is no more current in the circuit. So this will be it for the video where we have our introduction to the circuits with the capacitors in parallel, capacitors in series, and the capacitors with the resistors. There will be more circuits with the capacitors and the resistors in the future videos. And thank you for watching this video, and I will see you in the next one.